Hi there, it's Mr. Baker, and today we're going to be looking at sound and light. Okay, so today we're going to be able to describe that sound travels at different speeds through different materials, and then try and explain that, and then evaluate the advantages and disadvantages of communicating with light or sound. So you've all seen a lightning strike and you've heard the thunderclap that comes just after it. So why do you think that the lightning comes first? And then after that we hear the crash of the thunder. Hopefully by the end of the day you'll be able to explain why that is. Okay, so I'd like you to have a little look at the list of words down here. These are hopefully words that you've seen before. And then we've got two of our words. So we've got sound and light here. These words here link up to either sound or light. What I'd like you to do is have a little think about which words you think link up with each of those things. Have a go at doing that. And then I'll show you the answer in a second. Okay, let's go through this list together then. So let's start off with the sound. So sound, we've linked here to the first one, pitch. We normally talk about the pitch of a sound. So the pitch is like the frequency, is how high or how low the note might be. So like high or low the note might be. That would be the pitch of the sound. And we don't tend to talk about the pitch of light. We talk about the echoes of sound. So that's like the reflection of sound really, but it's the echo we call it rather than the reflection. We need particles to vibrate for sound, and so that's why we've linked that one there. And then we talk about the loudness of sound, rather than, let's say, the intensity or something like that. Although we could sometimes talk about the intensity of sound, we tend to talk about something either being loud or quiet. Okay, so let's have a look at the ones linked with light now. So an opaque object is something that won't let light through. Something that's opaque won't let the light through. Lenses, we talk about a lens. Lens uses something called a refraction, which will change the direction of light to either focus it to a point or to spread the light out. And transparent objects are like the opposite of opaque objects. Transparent objects will let light through. We don't tend to talk about transparent objects for sound. We don't need to sort of talk about that kind of thing. Sight as well is linked to light. We don't see sound, we see reflections of light, and that's how we basically see stuff around us. Okay, so how does sound travel? I want you to think about that question while you watch this clip.
You can hear sound to metal. I'll show you. Put your ear up against a metal fence, then have a friend go to the other end and tap on it. You can hear the sound through the fence ear before your other ear. Sound travels 18 times faster through metal than it does air. It's sound.
Here's another cool experiment. Put your ear up against a brick building. Now have a friend go around the corner and tap real softly. You can hear the tapping through the bricks. Sound travels faster through bricks, too. It's science.
It's sound.
Science.
Sound.
Science.
Sound.
So we've just seen that sound travels faster through solids than it does through air, and we're going to see if we can explain why that might be. But first, let's have a look at how sound actually travels at all. So we've got a vacuum. This is a normal sort of demonstration that you might see. You've got a vacuum pump. A vacuum pump is something that can either pump air in or maybe suck air out of something here, which is a bell jar. So it's a jar in the shape of a bell. And then inside that you've got an electric bell, which is hanging up here in this case, linked to a battery. So we could basically switch this bell on, and then with the vacuum pump we could pump the air out to make a vacuum inside here. And we're going to have a little look at that, and I'd like you to think about this. What do you notice as the air is gradually extracted, and why do you think that might be? Okay, so here we've got that same setup. We've got the vacuum pump, and we've got our bell ringing inside this vacuum, in this bell jar. And at the moment we are pumping the air out and creating a vacuum. Can you hear what's happening? Okay, so it's got quieter, quieter. You can't quite hear it, I suppose, because the vacuum pump's going quieter, quieter. So here then, before we move on, so we pump the air out and you can hear it get quieter and quieter. And at the moment there's pretty much no air inside here, so this is a vacuum now. And you can see that the sound has got virtually impossible to hear. Let's see what else happens after that. Okay, so the air's been pumped out, we can't hear it. Now what we can do, we're going to turn that off, so we're not pumping the air out anymore. Now we're going to let the air come back in. Just change the valve there, let the air come back in. Okay, so the air's coming back in, and can you hear what's happening? So as the air goes back into the bell jar, the electric bell is getting louder and louder. Okay, so why do you think that is? Why do you think that the bells get louder as there's more and more air in it? Okay, so here's a diagram of it. When there's air inside, you can hear the sound, and when there's no air inside, you can't. So what does that tell us? It basically tells us that we need particles for sound to travel. Without particles, sound won't travel at all. Okay, so we've seen a few things now. We've seen that sound needs to travel through particles, and it travels faster through solids. So let's have a look at the difference between different things and see why it might travel faster through a solid. So this is a question we're basically asking: why does sound travel at different speeds through solids and gases? And we can also say that it travels at different speeds through liquids as well, though we haven't seen that yet. So have a look at this diagram here. So we've got a solid, a liquid and gas. I'm sure you've seen a diagram that looks like this before. In a solid, the particles are this nice fixed shape. They're really close to each other. In a liquid, we've got a similar kind of distance between the particles, so they're slightly more spread out, but there's no sort of fixed pattern. And in a gas, all the particles are far apart. And this is really the reason why sound travels at different speeds. When the particles are close together, it's really easy for them to knock into the next ones. In a liquid, it's not quite as easy, and in a gas, it doesn't happen as quickly at all. So these particles got to move that distance before they hit into the next one. And that's basically what happens. A sound is this movement of particles created by something, and then the sound travels through depending on how closely the particles are. So in solids, the particles are very close together, and in gas, the particles are far apart. So the sound travels fast through solid and slow through gas. So let's come back to this question we started at the beginning. Why do you see the lightning and then hear the clap of the thunder afterwards? Well, so it's really all to do with the speed that these things travel. So light travels at 300 million meters a second. That's 300,000 kilometers every second. Just think about that, 300,000 kilometers every second. That's really, really fast. In air, sound travels at 340 meters per second. So it travels a lot slower. So when the lightning happens, we see it almost instantaneously because it travels so fast, but it takes time for the sound of the thunder, which is basically the ripping of the air because of the lightning. And so it takes time for that sound to reach our ears. So the last thing we said we'd do is look at the advantages and disadvantages of communicating with sound and light. So there's things you might think about, but I'd like you to think about these ones. So if we're communicating with sound, some advantages might be that we can use language quite easily to communicate complicated things in the way that I am right now. and it's really easy to do over short distances. But some disadvantages might be that noises can make sounds difficult to understand. Over large distances, it's actually quite slow, like we saw with the lightning. And over large distances, it can't be heard very easily as well. So if you're further away than you can actually hear the sound, then you obviously can't communicate with it. Now, communicating with light, some advantages are that light is really, really fast, and we can actually use lots of different, we call them frequencies or wavelengths, to code really complicated communications. So this is how we communicate our phone signals, it's how we communicate radio, it's how we communicate computer signals and broadband and things like that. They all use types of light to basically communicate like that. Some disadvantages though with light is that if you are going to do that, unless you're using something like semaphore or something like that, you need to have specific applications to send and receive the signals. And even with something like semaphore, then you need to have a code to communicate it. So you need to know it's not just as easy as I'm doing talking to you right now. Okay, so that's basically the lesson today, sound versus light. Hopefully you've been able to do most of these things, describe the sound travels at different speeds and explain why, and then to think about some of the advantages and disadvantages of communicating with light or sound. Okay, thanks very much. That's me finished for now. I'll see you next time. So I said I'd finished, but actually I just saw this and I thought it would be useful. So we talked about why sound travels differently between solids, liquids and gases, but this is a really nice animation that shows it. Imagine you've got 3 lines of dominoes. In the first one, the dominoes are all really close to each other. If you knocked one, they'd all go really quickly. If you had dominoes that were slightly further apart, then they would travel a bit slower, and if they were even further apart, they would go even slower. And that's basically the difference between solid, liquid and gas. It's a really nice, easy way to show the differences between them. Right, so that really is it this time. Thanks for watching. Mr. Baker is out. Thanks very much.